طيب بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Today's lecture is the last one in topic number 2. So we're going to be wrapping up this discussion on modeling rigid bodies. Today's actually a very important lecture, and we're not going to have any new material. We're just going to take the old material and try to understand it more. So today's lecture, we'll see, inshallah, will be a little bit slow-paced. We're going to be covering, again, as I mentioned, the same material that we had, but hopefully we're going to be connecting all of the dots together. As I suggested, if you really followed the homework and the assignments, or at least try to start, and you really started studying the previous lectures, today's lecture will really connect all of the dots. I think you can get out of the lecture, with a really good understanding of rigid bodies. If not, then hopefully when you rewatch the video, you'll see, okay, how everything start to make sense. Rigid bodies are very important because they are the building block that we're going to be using in the course. Starting from next topic, we're going to be seeing how we can use this building block and all of the stuff that we're discussing today, and in the end, model complex robotic systems. So this is the whole idea. And the level of complexity, so you can actually do as much as you can in the project. That's why in the end, okay, if we have some time, we can talk about the project and what you should expect in the coming weeks. So that's the plan. Okay, so let's start. So we only have today in-depth analysis of what we had. Okay, and just a recap of what we discussed so far. So this is the scenario that you will find yourself in. You have a robotic system that, and you start putting frames everywhere. And the relative pose between every frame is simply given by a member of SE3. It's a homogeneous transformation matrix that has the pair R and psi. So R is the relative orientation between the two frames, and psi would be the origin of frame I expressed in frame K. Beware that this is frame I expressed in frame K. So the K is on top. Okay, so this is where you're expressing stuff. And then we said that the point dynamics, if you have only rigid, if you have points, that don't have any frames, so this is usually the setup that you're familiar with from mechanics, from basic mechanics, is that you have the configuration is given by this relative displacement between B and S, and you have the rate of change of the configuration, is the psi dot, and the velocity expressed in S is simply the rate of change of the position. Okay. And this is, you only have one frame here, which is the reference, the inertial frame, and this is where you refer everything to. When you have orientations, you have two frames. We have the configuration there to be an element of SO3. The rate of change of the configuration is another matrix. So being a rotation matrix means you have constraints. You cannot be any numbers. And we saw that, for example, we need to have that the transpose is the inverse, and you need to have the determinant to be exactly +1. And this is another 3x3 matrix that corresponds to the rate of change of the rotation matrix, and itself it has some structure, and we saw that in the space in the structure of this tangent space at the point R. And then we had the angular velocities. We said that they live at the tangent space at the identity, which was what we called small SO3, being the Lie algebra of the Lie group as capital SO3. And we have two versions of this angular velocity, two natural ones, which physically would be how we do represent the angular velocity in the B frame or in the S frame. Okay, so you have the body angular velocity and you have the spatial angular velocity. Being in SO3 was the space of skew-symmetric matrices. So being in this tilde form, the omega with the tilde was simply a skew-symmetric matrix. And following the same idea, we found that we can do rigid body motions, which are combined rotations and translations, by looking at an element of SE3, and the rate of change will be, again, a vector in the tangent space. And when we look at the algebra of SE3, we find that we have what we call twists in this tilde form. And then we also have the kinematic relation in this way between H dot and V tilde. And the V tilde here, if it's in the body frame or in the S frame, it changes how you relate it to the H. So you can either have left translation, or right translation, or which in the end translates to left multiplication and right matrix multiplication. So everything you see here are matrices, but you just need to be aware of what is the objects that are behind it. And from that structure, we said that skew-symmetric matrices are isomorphic to R3. Okay, so here we have a 3 by 3 matrix, but in the end, it's equivalent to just 3 numbers. What can we say about an element of SE3? We found that it always has the structure. It's always a skew-symmetric matrix here. The bottom row is simply zeros, and we have here the 3 elements that we call linear velocity. Today, inshallah, we're going to be focusing a little bit on what's the nature of this linear velocity. But in the end, this 4 by 4 matrix can be simply written as equivalently for the 6 numbers, the 6 tuple, okay, that we call, the vector. So if this is you can, when you're studying, this is how you think about it. This is the matrix representation of the twist, and this is the vector representation of the twist. But don't forget, okay, but in the new terminology, this is a vector and this is a vector. Actually, both are nothing else than a representation of the algebra element, okay? So whether you write them like this or like this is just the way how you put numbers together. But in the end, they correspond to the same abstract concept. This is something we're going to be focusing on a little bit today. Yes? Going back and forth, you mean? No, this S tilde, you mean? This is just the name of the map. If we call this S, we can call this T, F, X, any symbol, exactly. It has nothing to do with the fact that it's actually a tilde. No, that's right. Okay. The tilde is simply is a general map that would take. So the tilde that you can also call it the tilde map or the S map. In the literature, they have actually there's a more common way that people a lot in robotics use. They usually call this the hat map, and they call this the V map. So hat, you find it's like this, and the V is the opposite of that. Okay, so sometimes they map this from here to here by hat, and they usually use, instead of the omega tilde, they use an omega hat. Okay, this is usually a common notation in the literature. Okay, I prefer personally the tilde. Okay, so you have here, going from here to here, you have the tilde form, and here is the inverse tilde form. Okay, and here we call this map S, and it's not only for angular velocity, it's even for any R3. Any R3 in the end, you can put it in tilde form. There's a problem in the homework or in the assignment, I don't remember, where you can actually show that this skew-symmetric form, if you multiply this skew-symmetric matrix by any 3 numbers, did anyone solve the homework? What was the result? What? But what was the operation? If I give you omega 1 and omega 2, and I tell you, make omega 1 into the tilde form and multiply it by omega 2 in non-tilde form, what is the result? It was the cross product between the 2 vectors. Okay, so this whole idea of this skew-symmetric matrix is also related to the cross product that we never discussed here. When you have vectors, you can do the cross product. You can do the inner product, and you can do the cross product, and you can find in the homework that is actually it's already taken in here. Any questions so far? Okay. Now, we have, similar to what we had earlier, that we have an angular velocity in the body frame and an angular velocity in the spatial frame. We can also have a body twist and a spatial twist. So the body twist is nothing else than the twist. So it's the generalized velocity of frame B with respect to frame S expressed in frame B. While here you have the generalized velocity of frame B with respect to frame S expressed in frame S. So the only thing is that we have here how we represent the numbers, where we represent this vector, this abstract concept. And you see here that the map, we showed it last time, that's called the adjoint map, and the adjoint map has exactly the structure. You have in the assignment where you can actually derive and show for sure that this is what comes out from just comparing these 2 expressions together, okay, and in the end, just matching the components there. So this is what's known as the adjoint map of SE3, and then we said that the adjoint map, it has very nice properties. First of all, it has composition. So if I compose the adjoint of one H with the adjoint of another H, is equivalent to the adjoint of the H1, okay, the group product between H1 and H2. And then you have that the inverse of the 6 by 6 matrix is nothing else than the adjoint of the inverse of the H matrix. And you all know that the inverse of the H matrix had a special structure, that it had the R transpose and minus R transpose multiplied by the size. And the time derivative of the adjoint matrix is equivalent to the adjoint matrix itself with the same indices multiplied by the small adjoint, which is what we called the adjoint operator of the algebra. And this is a function here of the twist. So if you give me the twist, which will give me the 6 numbers, 3 on top, which is the angular velocity, 3 on the bottom, which is the linear velocity, you find that the adjoint has this special structure. It has the omega tilde, v tilde, 0. Okay? So this is usually what's known as the small adjoint. These are all of the math that you need to actually start doing robotics. So to start, not really to do, okay, just to start, okay? Don't take me literally, okay, yes?
But has the ability to change the code?
That's right, yeah.
So,
very good question. We'll have it today. Yeah. It does change coordinate in a specific way. You'll see it today, inshallah. Yeah. So when you want to do the dynamics of translation, of translating point masses, in the end, you just have a kinematic relation between velocity and the position. And you have that the rate of change of the momentum. How is the momentum defined? Is simply the inertia multiplied by the velocity. And here, the rate of change of the momentum in an inertial frame, you always need to choose an inertial frame. You cannot define the dynamics, Newton's law, okay, in a non-inertial frame. You need to always have an inertial frame S. The rate of change of the momentum here will be equal to the applied force. Of course, these 3 equations, in the end, you just usually combine them together and you get the familiar form F equal to ma. Okay, so F is equal to mass multiplied by the acceleration, where the acceleration is the second derivative of the position variable, psi b from S. And when we look at rigid body dynamics, using these tools that we have, okay, working on SE3, everything that we have here is simply 6 numbers. How can we start doing the same, okay, so mimic the same nature, and exactly what you saw there will be here. You have a kinematic relation between the velocity being here, the generalized velocity being the twist, and the pose of the rigid body. You have that the rate of change of the generalized momentum variable. So we introduce something called the generalized momentum, P. And this generalized momentum, when you take the rate of change of it, you'll find that you have all of the applied wrenches up on the body. And the wrench here is a generalized force. It has forces and torques, just like how the momentum would have linear momentum and angular momentum. And the twist has linear velocity and angular velocity and so on and so forth. There's always a convention. The convention we're using here, the rotational stuff on the top and the linear stuff are on the translational stuff on the bottom. Okay, so we always have this. Don't mix them up. Okay, again, this is a convention. You'll find some literature, okay, that actually split them up. Okay, you can actually have the translational parts up and the rotational parts down. It's just a choice. Okay, so some of the classic books, the one by Lee, Murray, and Sastry, actually, okay, they sometimes have this other convention. So be aware when you're looking into different literature. And the twist is related to the momentum simply by this generalized inertia matrix. So the capital I here is a generalization of the idea of inertia, okay, in one dimension, where you start to have now more, okay, effects because you're doing translation and rotation at the same time. So P is the generalized momentum, the W is the resultant wrench, the generalized forces, and I is the generalized inertia. Okay. Now what we're going to be doing is that we're going to be going into details, okay, about some of this stuff. So hopefully, okay, you'll be able to connect the dots. First of all, if you remove where you express stuff, all of this idea of where you express stuff, you'll find that in the end, these are the 4 abstract concepts that we introduced. One, which is the generalized velocity of the body with respect to the fixed world. And this is simply V, B down, S up. There is no expressed in. Okay? And then you have a momentum, which is generalized momentum of the body. You have a generalized force, which is we call the wrench, and you have the generalized inertia of the body. If we want to relate them abstractly, you say that I have this living in some space, let's call it V. This is just an abstract space. It's a vector space, but it's abstract. It's not numbers. It's not 6 numbers, just V. The momentum and the wrench will live in V star. So they are covectors. And the inertia, okay, will be what we call a 0-2 tensor, okay, which is simply what we introduce as bilinear map that eats a vector and spits out a covector, okay? Why is it a bilinear map? We said that there are two types of, okay, we said there are actually four, but only two of them are interesting. One, which is that eats a vector and spits out a covector, and another one that eats a vector and spits out a vector linearly. Of course, both have to be linear, okay? And even the V star itself is something that eats the vector, but spits out the V star is a linear map that eats the vector and spits out a number, a scalar, exactly. Okay, so we had these, there are actually three types of maps here. There is the I that eats a vector that goes to a covector. We called endomorphisms that eat a vector and spit out another vector. And you have here covectors that would eat a vector and spit out a number. Okay, you remember it was the endomorphisms, inside of it was the automorphisms, and you had the V star. This is the special case here. Now, if you look at as a vector space abstractly, this still makes sense. 0-2, yeah.
How do you classify it? This tensor type?
We haven't discussed it, but I'll tell it to you. So it's not something we discussed, but endomorphisms are usually 1-1 tensors. Okay. Bilinear maps are 0-2 tensors. Vectors are 1-0 tensors, and these are 0-1 tensors. Covectors are 0-1 tensors. And you can have higher order tensors. You can have 0n or 1-3, 2-3, and they appear everywhere, okay, in physics.
It's not bilinear or endo, it's something else.
They are called multilinear. Okay, that's where we go to higher for. They are used in robotics, yeah. Okay. But at this point, at this stage, we can do everything with only second rank tensors. They're usually called second rank tensors. Usually have them in more advanced stuff if you really want to do stuff. In physics, they appear a lot. Okay, if you really go outside of robotics. So V is a vector space because it has the zero. The zero twist here, what does it mean? No motion, no general motion. The two bodies are fixed. I'm not talking here about frames, by the way. We're talking here about, you see, the velocity of the body with respect to the fixed world. For example, what is the velocity of this phone? See, okay, this is it's doing like this, or it's doing like this, or it's doing like this. You see, I give you three ideas. You can, of course, it can be the other direction, and you can have all sorts of combinations. So actually, this is the abstract twist, okay? Because the phone is the body we're talking about here, and it's moving with respect to the fixed world. Whether it's with respect to the table or with respect to the ground, it's the same thing, right? Because the table and the ground themselves, they actually have a relative twist of zero. So you see, this is exactly what the abstract zero means. It doesn't have any numbers. It's not 0, 0, and 0. It's just one abstract zero. So there is no motion. And simply, you can also add two twists together. For example, this is exactly how you've been introduced to mechanics. In the first time you took it, you talked about velocities. My velocity with respect to the phone, okay, is exactly the phone's velocity with respect to the table, and the table velocity with respect to me. This combination, of course. You have to take care of the pluses and the minuses. So actually, we also have a minus here, because if the phone is moving like this, then I'm moving like this with respect to the phone, right? So there is a positive and there is a negative. And if you sum them together, you get zero, okay? That's what we're talking about, two relative things. So we have all of the stuff that abstractly would make up a vector space. So you see, there's no numbers here. Yes, exactly. Car A, velocity of car A with respect to you is the velocity of car A with respect to plus the velocity of car B with respect to you. That's it. You see, that's exactly the summation here. And it's by the way, it makes sense. It's something physical. It's just that when you took this idea and when you went to rotations, okay, in a wrong way, or in other words, when you combine the rotations and translations separately, you found that this is no longer true. And that's exactly what twists do. They actually put back this simple concept. I'm going to show you today, hopefully by the end of the lecture, okay, why is this? Okay.
Can I leave it like this like this?
That's a good question. The forces, you mean the wrenches? The wrenches, they live here in the V star, which is itself a vector space, which means I still can add them. You can add wrenches. Yes, of course. For example, so I have my hand pulling this down, my right hand pulling this down, and my left hand pulling this up. So what is the resultant wrench here? No. It's my hand, my right hand plus my left hand as a wrench. Very easy. It's just summation. I'll give you another example, which is something we're going to be seeing later on. You have a drone. You have a body of a drone. And the drone has 6 propellers. Each one produces a wrench. What is the resultant wrench on the body? 1 plus 2 plus 3 plus 4 plus 5 plus 6. Done. Full stop.
Since so when you said 1 inch is put into 1 wedge is put into
Yes.
it have a negative sign.
That's a good question. That's an excellent question. Of course, it will have some signs, okay? Because you have to actually represent the wrench first in one frame. And then if you start to add them together, what was the constraint? You remember? They have to be expressed in the same frame. When you express the forces into the same frame, you start to get the whole idea that you already know about, that if I have a force at a distance, what comes? A torque. And when you also have angular velocity and you look at a distance, what do you get? You get linear velocity, tangential velocity, right? All of this will actually make sense. Where is all of this captured here? Does anyone capture that or guess? Can guess? What is the thing here that captures all of this taking a force and translating into a torque, or taking an angular velocity and making it into a linear velocity?
Bilinear math, I think.
It's something here in the board. Something in that joint. The psi hat. Psi hat is what? You take a position vector and you make it into a skew-symmetric matrix. And if you multiply the skew-symmetric matrix by 3 numbers, what is that equivalent to? The cross product. When you transform a force to a torque, what do? You take the cross product with the position. When you transform an angular velocity to a linear velocity, what do? You do a cross product with the position. That's exactly the term that is, okay? And more on that later. We have some, okay, hopefully we had at the end some more equations to show you that, okay?
Some of the cases we have frames that have an effect on other frames.
And what, like what?
Can we see the wing as a frame?
Yes. Yeah. For example, if you have an airplane, you have air applying a wrench on the wing, and the wing is attached rigidly to the body. So yeah, you can model the aero effect, the wrench applied from the air on the wing, and then transform it to the body. That's exactly actually what we're going to be doing to derive the wrench applied from the propellers on a drone. We'll do that. So you'll see it later, inshallah. It was part of the assignment, but I removed it, out of pity. Okay. So now this is the abstract stuff. Okay. There is here also something related to when you have a momentum, how is it related actually to the velocity? We said that the generalized inertia will eat the vector and will spit out a covector, which is the definition of the momentum. And also, if you take this momentum and because it's now a covector, and I can make it eat another vector, if it eats the same vector that generated it, last time we showed you that actually this is twice the kinetic energy of the body, abstractly, without any numbers. And here, the wrench, when you make it eat a twist, what do you get? You get mechanical power. So the numbers here that represent, in the end, they are either kinetic energy or power. So they're just scalars that you can compare to each other and so on and so forth. Okay. This is just a special notation. Okay, you'll find it here introduced, and it's also in the reading material. Take a look at it at your own pace to conceptualize it. So this is abstractly without any numbers. How do we introduce numbers? You need to do basis. You need to choose a basis for the vector space. How do you choose the basis? It's simply this object, the frames. Okay? You need to say that I have a frame that has X and Y and Z placed at the body, and another one placed at the table, another one placed at the base of the robot, another one placed here and here and here and so on. You start to add all of these frames. And by doing that, let's say that you call this frame, okay, M. So this is your basis. So in the end, the V of B with respect to S, the abstract concept, if you express it in M, it's exactly as taking this vector and looking at its components in the basis M. So if you remember from the vector space, okay, lecture, when we had a square bracket and we wrote down the basis, this was actually the components of the abstract vector. Okay? You need to start studying. That's actually why you have a quiz next week. Okay, so this is the components of the abstract vector. So the V in the expressed in M is the components of the twist. The P expressed in M is the momentum of the body expressed in M. This is the wrench applied on the body expressed in M. You see here the B's and the S and the B to S, they are all the same because they're abstracted. And where you express stuff is all of the green stuff here that's in M. They are all just depending on the basis. And if you can choose one basis, you can choose any other one. So that's why you can always transform from one basis to the other. For example, here, these are all of the formulas that you need to transform from M to K, from any frame M to any frame K. Okay, it's either from B to S or from S to B. It doesn't matter. Okay, or even from to a third frame that's neither on the body nor on the inertial frame. Okay? It can be anything.
6-dimensional or 3-dimensional?
The basis was simply 3 directions, okay, and a point. This was what the basis.
R6.
Yes.
At the end, it is 3-dimensional basis.
Because you had three angular velocity components and 3 linear velocity components. Okay. So how do you rotate around this and that, and how you translate in these 3 directions? This was, intuitively what they mean. And these were their change of coordinates. If you look at them, you find that the V changes coordinates by the adjoint, the P changes coordinates by the inverse transpose of the adjoint. The wrench is the same exactly because it's the same nature. And by the inertia changes coordinates from the right by the adjoint, from the left by the inverse transpose. Okay, this is exactly the same formulas that were again in the homework number 2. Okay, and you can also, because you see here we have the minuses. Okay, we have an inverse, we have an inverse here. Another way of actually looking at it, which is exactly equivalent. You remember we said that if I have the adjoint of H from M to K, and I would write this as the adjoint of H from K to M, what would be the relation? It would be the inverse. So if you can either put everything here from M to K or write it from K to M, but you're gonna have either if this one will have the inverse or this will have the inverse. And here these 3 they will have the inverse and these 3 will not have the inverse. We just one or the other. Okay. Yes.
Working on the Mock 2, you said we should do a particular problem where Rn by n
Yeah.
is a linear isomorphism with Rn squared.
Yes.
This R6,
Yeah.
basically, where we have 6 stuff, is it a representation of Rn squared? Can we say it's Rn squared?
No, it's not. It's the 6. So the number 6 is not the square of any number, right? It's not the square of any integer. So that's something else, right?
It's like X, Y, and Z and the orientation, Euler orientation, the coordinate.
No, I know.
The X, Y, Z, right?
The V you mean?
Yeah, the coordinate itself. I mean the coordinate. It is X, Y, and Z in this coordinate.
No. There is no X and Y and Z here. You mean the directions? There is angular velocity in X and Y and Z and linear velocity in X and Y and Z. There's no Euler angles. Okay? Here. Okay? They're just velocities. The twist is velocities. The momentum.
This is choose it. X, Y, or E1.
You'll see exactly, hopefully, if we have time if we reach that far, you'll see today what is inside of the twist. Okay? So hopefully this is actually on the list now. Yes. Yes.
I get rid of the inverse.
Yes. Let's see. I think, yeah, I think there's a.
Should be the same.
HM, yeah, I think you're right. Yeah, I think you're right. Yes, this is actually a type. Yes, thanks a lot. It should be exactly the same. So this is just a choice, You can either, the reason why I write these two is that if you want to memorize them, if you really want to, put them and engrave them on your dorm wall so that you can never, forget them, because you're going to use them again and again and again. Okay, so I'll just correct it before you engrave. Okay. This is generalized inertia. Okay, the generalized inertia is always symmetric and positive definite. That's one of its properties. It is constant if you represent it in frame K, any frame. It will always be constant if K is any body fixed frame. And these are three examples of body fixed frames you see there. Make sense? Okay. These are all three body fixed frames. Whenever the body rotates, the frame changes width. Even if it's not on the frame, even if it's not within the body itself. For example, you can tell me this is the body and this is the body fixed frame. They move like this. You see? They move like that. They're always moving together. Okay, so this is a body fixed frame. If you represent the inertia in any one of these frames, you'll always get a matrix that looks like this. You're going to have the J on the top, the M, okay, just redundantly multiplied by an identity matrix here, and here on the diagonal you have the location of the center of the mass. If you choose the K to be at the center of the center of mass is a physical point, okay, because it's the point that you can replace all of the points there, okay, with an equivalent, okay, mass at this point. So here you're gonna get, okay, a matrix looks like this, where the off diagonal term will just drop out. Okay, and the J itself is not diagonal. Okay, it is actually a 3x3 symmetric matrix itself. And in practice, usually, how we get this stuff is, using just SolidWorks. You take your robot and you plot it and you draw it on SolidWorks, and you'll tell it numerically, calculate for me the center of the moment of inertia, and it will tell you the J. It will give you 6 numbers corresponding to the J. The 6 numbers are actually the independent components here of this 3x3 matrix. It will tell you where the center of mass is, and it will tell you the total mass. Okay? But it will also tell you where the inertia, which coordinate, okay, you're choosing. Okay? That's why it's confusing for some people actually when they use SolidWorks. And you have to do it actually for yourself if you really want to learn about it. How do you get this information from SolidWorks? Okay, just draw something and see what you get there. Okay, you can search on SolidWorks for mass properties, and this will spit out for you the moment of inertia. Sorry. Now, this is what we're going to be doing hopefully in the next, okay, half an hour, okay, is that we only talked about the rate of change of momentum in the S frame, right, in the inertial frame. It's very common that we write the equations of motion in the body frame, in the body fixed frame. So how would the simple equation, that rate of change of momentum equal to wrenches, look like when we go to the body fixed frame? That's the first thing we're going to be doing. And then we're going to be doing something that, okay, it's very common, which is splitting rotation and translation. Okay, can we always do that? That's the question. And how is this related to more common forms where you actually, if you read a paper, where actually you're going to find this equation of rigid body, how it's commonly written. And the last thing is, what is the twist? Okay. And by twist here, I mean, what is the nature, of this object that we're using, this V, capital V, that we're using all of the time. We're going to be looking at it in more details, hopefully, if we have the time. So we're going to have a lot to write today. Okay, so let's start. So the first thing we're going to be doing is writing the momentum balance in the B frame, not in the S frame. Okay. So the equation that we have is simply P dot of the body attached to the B frame, but expressed in the S frame. And this is equal to the wrenches applied on the body expressed in the S frame. Here we had the total. Okay, but we're just going to drop that total, just as a subscript from now on. Okay. So this is the first equation that we have. And what we said earlier is that any covector would transform coordinates in this way. So we have that the wrench is given by this expression, and the momentum is given by this expression. Make sense? Everyone agrees? Okay. This is how we transform a covector from one frame to the other. Both are covectors, so we have the same. So if you take in this expression here and you plug it in there, then actually, so this, let's call this equation 1, 2, no, sorry, let's call this. Let's call this equation 0. This is 1, and this is 2. So now if we take equation 2 and 1, and we substitute them in 0, this is what we get. We simply get that the d by dt of this expression, okay. Oh, let's see. Yep. Is equal to that expression. Everyone agrees? Okay. Now this expression itself, okay, I have a matrix multiplied by a vector, and I'm taking the time derivative. How can you expand this? By Leibniz rule. Okay. I take the time derivative of the first multiplied by the second plus the first time derivative of the second. Okay. So this is actually, I can rewrite this as d by dt of the add multiplied by p in the B frame plus the add multiplied by the P dot equal to the one on the top. Make sense? Okay. Sorry? We'll come to that. Yeah, exactly. But first, what we can do now is that we can multiply both sides by the inverse of this matrix, you see? Okay. So we're going to multiply both sides. So we have this equal expression and this expression. This is equal to that. So we're going to be multiplying both sides by this. So in the end, what we get, okay, by multiplying both sides by the adjoint from S to B, but the inverse transpose, we get this equation, which is P dot is equal to the wrench applied on the B frame minus the adjoint inverse transpose from S to B multiplied by d by dt of the adjoint S to B transpose multiplied by the momentum. Okay. Let's just highlight this because we're going to come back to it later. So we're going to call this equation 3. So does it make sense for everyone? So if you compare equation 0 to equation 3, what is the first conclusion that you get? So what do you say? Yeah. Yes. Yes. That's a good question. So if you multiply this matrix by this matrix, how should it be the identity? Okay, so maybe actually because I think there's a typo here. Yeah, there's a typo. That's why. This should be S to B. Okay. This should be S to B. Yeah. That's why. Yeah. Now it makes sense? Okay. Clear for everyone? Okay. What is the conclusion that you get here? That when you say the rate of change of momentum is equal to the wrenches applied on the body, it's only valid in an inertial frame. Because if you transform it to a moving frame, which is in this case the body fixed frame. The body fixed frame is moving, right? It's moving with the body as the motion is happening. So you see we get this extra terms. What we're going to be doing now is just a massage, okay, for this term. We're going to just rewrite it into something that, okay, different ways, okay, that you actually have been introduced to all of them earlier, okay? So what we're going to be doing now is that we're going to be splitting into two parts. So first, we have that, this is a property, okay, that the d by dt of the adjoint, does anyone remember how it was look like? The adjoint itself, same indices, multiplied by the adjoint, small adjoint for a twist. How do you memorize the indices here? You start, if this is S to B, this is S to B. And where is it expressed? In the lower index. That's it, okay? And I can play around with this expression, okay, in different ways. So we're gonna rewrite it as like this. And make sure this makes sense to you. Make sense? Swapping from S to B becomes B, negative B to S, okay? Something that you can check for yourself. You've seen how the adjoint looks like, right? The adjoint itself was consisting of just skew-symmetric matrices, right? You take the components of the twist, and you take the linear part and the rotational part, and you start putting them into, you know, skew-symmetric matrices. The skew-symmetric matrix is actually a linear operator, okay? It's actually a linear operator. So if the adjoint is made up of just the skew-symmetric operator, this S map, so in the add itself is actually a linear map, that if you apply to it a twist, it will give you actually back, okay, the twist linearly. So it maps linear, okay, the twists. Which means that if I have here, if this is not minus of the twist, if this is just -1 multiplied by a twist, so there's a number -1 multiplied by the twist, and this is a linear map, what is the result? When you have if you had, for example, f of alpha multiplied by v, and f is a linear map in this vector space. The alpha goes out, so this is equivalent to alpha multiplied by f of v, right? That's exactly what we're going to be doing here, because this is a linear map. This is actually equivalent to this expression. Okay? So far, so good? So we're going to be leaving this, and we're going to be calling this equation 4 for a while. And now we're going to have another property. So this is a property that we started with. Another property related to what Tariq was asking about, which is if I have the adjoint map itself, the small adjoint, and I want to change the twist inside from one frame to the other, how does this change coordinates? And the answer is that it changes by this expression. If I have the adjoint of V star with respect to circle expressed in frame M, how is this related to the adjoint of V star with respect to circle expressed in frame K? What is star and circle here? Any frames, okay? They don't affect at all how you change coordinates. Why is that?
So they are appended.
Nope.
Was there stationary?
Nope. No constraints on them. They're not stationary. They can be any frames between frame I and J, X and Y, any frames. But why is it that only when we change coordinates here, I go from the M to the K? Why is it only these indices that change coordinates? Because that's only the observer. You remember what we said about the abstract concept and the components? The abstract vector itself does not change. It's exactly the same abstract vector, which is the relative, here in this idea, is the relative twist between the body attached to frame star and the body attached to frame O. It's not changing coordinates. It's something that's abstract. Only what's changing coordinates is where I express these coordinates. This is the only thing that has the basis. And that's why this is the index that changes. How does it change? By an adjoint from the right and adjoint from the left. And if this is from K to M, this will be from M to K. Okay. Or I can, if this is from M to K, I can write this as M to K and I put here what? An inverse. So what does this look like to you? What was the thing that changes coordinates by P inverse, and the matrix itself is in the middle?
Similarity matrix.
What we called it? An endomorphism. Endomorphisms change coordinates like this. So it's a 6x6 matrix, but it's not like the generalized inertia. The generalized inertia is a bilinear map, and this is actually an endomorphism, just because of the way it changes coordinates. Okay. So now if we take this expression, by the way, we can also play around with it and write it like this. Take a look if you agree that this is actually equivalent to this expression. So these are just the same equations. They're just a property of the small adjoint. What we did here is that I took this matrix and I brought it this side, okay, by its inverse. And because this will be an inverse, it will change coordinates from K to M, it will be M to K. So you see here I have add from M to K. On this side I have add from M to K. And here I have the adjoint expressed in M, here the adjoint expressed in K. And here instead of the star and the circle, I just call them I and J. Okay. If you want to, so that you're not confused, let's go back to the star and the circle. So star, circle expressed in K. Okay. Yeah. From the left, you mean? This one. This is here. This is this one. And what the adjoint that was here, we put it on the other side with an inverse. That's exactly what we did. So these are the same expression. Okay? Same property. Not yet. No, there's no derivatives here. It is just the property of how we change coordinates. Okay? You're going to see how we use it right now. I'm going to rewrite it again. I'm going to rewrite it into this form because it will be useful for us. If I substitute the star and the K to be equal to B and the circle and the M to be S, what you actually get is the following expression. And we're going to be calling this equation 5. Make sense? I wrote nothing new except just changing the name of the indices. Okay. So now what we're going to be doing is that let's plug 5 into 4. Yes, exactly. If we plug in 5 into 4, you see that we can write that the rate of change of the adjoint is actually equivalent to, which was equal to, where was it? It's actually, so this was equation 4. So the rate of change of the adjoint was equal to this expression. But because I have an capital adjoint on the left and a small adjoint on the right, I can swap them and write them like this.
Second equation.
Which one here?
M and K, they are just observers.
Yes.
So changing them will not make a change. But here, now the observers themselves are
B and S. Yeah. That's okay. That's our choice. So here, when we say the star and the circle are B and S, then we're thinking about the twist of the body with respect to the inertial frame. That's the abstract object we're interested in. And when we say here frame B and when we say K is B and M is S, we want to transform from frame B to frame S or vice versa. That's exactly what this expression says. That's okay. That's exactly what we've been doing. That's exactly the body twist and the spatial twist, right? When you represent it in one of the frames. It can be any frame, including the B and S. That's the idea. No, it can be any frame. Okay. So this actually is equal to the adjoint multiplied by the adjoint S to B. So we're going to be calling this equation 6. Make sense? Okay. Make sense? Okay. So what we're going to be doing now is that we're going to be substituting equation 6 in 3. Okay. So what was equation 3? Let's go back to it. So this was equation 3. When we say that we have the rate of change of the adjoint, okay, and it's pre-multiplied by the adjoint inverse transpose of S to B, and this was the H from S to B, and this was transpose. We're just gonna take now the rate of change of the adjoint that we had, and we're gonna plug it in here. And again, play around with some math. So actually what we have right now is that P dot is equal to the wrench, and you have, this was what we had in 3 earlier. So that's exactly what was written before. This is the P. And now we're going to be substituting this expression. First of all, we had a minus, and there's a minus outside, it will become a plus. Okay. And then we're going to have this term, and this had its own adjoint coming with it, and then we'll have BS applied by the B. There is here something, okay? This is only the expression of the adjoint, the rate of change of the adjoint. Okay, so you have here the small adjoint and the capital adjoint. If this was transposed, what's the only thing that will change? This will become first, this will become second, and both of them will be transposed. That's it. Okay? If you have the transpose of this whole matrix, is nothing else than, so if you have, this is matrix A and matrix B, and if I take the transpose of A times B, what do you get? You get B transpose multiplied by A transpose. So that's exactly what you'll find in this expression, okay? And now you can see these two terms, what happens to them? Identity, why? One is the inverse of the other, okay? So in the end, they just drop out, and you're left with this expression, okay? So this actually is identity in 6 dimensions. So it's a 6 by 6 identity matrix. And in the end, you reach the final equation, which is P dot, so actually, you reach that. This is plus the adjoint transpose, and you have, sorry, this is actually something here not correct. Okay, this should be V, B, SB, SB multiplied by P, B. Okay, and we're done. Okay. So all of the complicated terms just boil down to this simple expression. Okay. So now let's do a summary. So the summary. So the rigid body dynamics in the B frame is given by, you have a kinematic equation that relates H dot to V, B with respect to S expressed in B, so the body twist. And you have that the momentum, the generalized momentum is simply the generalized inertia of the body, all expressed in the B frame, multiplied by the twist. Beware that this is tilde form and this is not tilde form, which means that this is a 4 by 4 matrix, 4 by 4 matrix, 4 by 4 matrix, while this is a 6 by 1 vector, 6 by 1 vector, 6 by 6 matrix. course, what I'm saying now is just numbers. You should always have in the background, this is a vector, this is a covector, and this is just, you know, a bilinear map that will take the vector and give you a covector. Even though we write them as column, you know, tuples, vectors, they have different nature. Yeah? And this is exactly what you've seen from the change of coordinates so far. And then we have that the P dot in the B frame is simply, instead of writing the wrench first, I'll write it second. So I'll write first the adjoint part multiplied by the momentum plus the wrench applied on the body. Yes. Okay. Now here there is a very important remark that actually where B is any arbitrary body fixed frame. Okay. So if this is your rigid body of interest, and this is the inertial frame, the spatial frame, and this is the body frame we're talking about, it can be anywhere, okay? Whether at the center of mass or not. So usually this is the symbol that you use for indicating where is the point corresponding to the center of mass, okay? So this is the center of mass, and the frame can be any place, can have any orientation. And these equations will always hold, okay? Make sense? Okay. You see here the momentum is completely, you know, redundant, right? We can actually write the equation without the momentum. And this is actually a more common way of writing it. If you take this equation, I can just plug in the momentum here, right? So I have here I multiplied by the twist. I can just put it here. And here I have the rate of change of the momentum. The I here in the B frame is what? It's constant. So when I take the time derivative of this expression, I just got the dot here on the V. So actually there's a simpler way of writing this equation, different way, that will look like this. So if we eliminate the momentum, you can actually write the equation as simply H dot is equal to H multiplied by V in tilde form, and you have here this expression okay. Which is another way of writing the same equation. This one is equivalent to the last equation we wrote it in the previous slide, and it's equivalent also to equation 0. All say only one thing: the rate of change of momentum is equal to applied wrenches expressed in a spatial frame. Okay, so this is the equation here. So this term, actually, you see now that all of these terms, they only appeared because B is a moving frame. Okay, it's not stationary. If it was stationary, all of this will drop out, as you just saw. Okay, and these equations, they actually have a very famous name. They're usually attributed to Euler-Poincare, and they're usually called the Euler-Poincare equations. Okay, so you're familiar with the Euler-Lagrange equations. These are usually called the Euler-Poincare equations of a rigid body. Okay, yes. Excellent remark. Yes, absolutely. Yeah, we'll see that right now. So we're going to be doing a simplification of this equation. Again, some massaging. And what we're going to be doing right now is that let's split the rotation and the translation. Okay? But we're actually going to be doing this by making a very important assumption. Okay? That we're going to be placing B at the center of mass. Okay? And in that case, the inertia matrix, I'm gonna drop the indices. Okay, you can fill in them later. So the I will be actually just J, 0, 0, and M multiplied by the identity, right? And if V now is equal to omega and V, so capital V here is the twist, small v here is the linear velocity component of it, and the wrench is simply torques and forces. And also don't remember that the H itself was actually a 4x4 matrix that had here, you know, a 1 times 3 and a 1 and the psi here. Okay. Of course, all indices, okay, where they should be. If you just take these equations and plugging in these ones, you can actually show for yourself that they are equivalent to the following equation. R dot, sorry, from B to S is equal to R omega tilde, and psi dot is equal to R B to S V. And then we have that omega dot is equal to, with a cross product, plus the torques. And then you have another equation in the V dot is equal to minus M, like, no, minus omega. You have the forces. Great. And you should have seen these equations at some point in your life. If not, you've had a, you know, not a very nice education. Okay. Before the assignment, okay. So exactly what Fahd pointed out, you've definitely have seen this term before, and also this one. You've been introduced to the one on the top under the name of gyroscopic torques, and the one on the bottom as Coriolis forces. This one, cross product. That's the one we're going to be using for the cross product, because we use the times a lot. We said when you use it to make sets and to make the Cartesian product and so on and so forth. So this will be the symbol we use here for the vector product, the cross product. So have you seen these equations before? Something similar, at least?
Derivative for the position till the acceleration at the end.
Yeah.
Will give us this.
Yeah, of course. It's a horrible way of doing this, physics. Starting from the position and then taking the time derivative and saying it's related, then you have the acceleration, and then you, right? That's it. Okay. Moving or not moving? Stationary. Okay. So that's an excellent question. What you're gonna get is that you're gonna get similar like this equation plus an extra expression that how does this observer change with respect to an inertial frame. And you will have another small adjoint with another twist. You're gonna have an extra term like this. Yeah. Yeah. So you actually have seen these equations maybe in a different way. Okay, because you see here, I have here the psi dot, right? And this is actually the V dot. So this is the time derivative of this V. Okay, which means that actually I can play around with this. You will actually have the chance, you know, to the pleasure in the assignment, okay, to actually show that in the end, you can take this equation and the rotational part would be exactly the same. We're not going to be changing the rotational part. So let's see if we can. Okay, we'll not be able to have it. Let me rewrite it again. So this is exactly the same part for the rotation. The linear part that was here, okay, I'm going to introduce a new variable, okay? I'm going to take this multiplication, this matrix R multiplied by this vector V. I'm going to be calling it something new. We're going to be calling it, so let's here call, let V bar, this is a completely new vector, 3 numbers that are calculated by just multiplying the RB to S by the VBSB. Okay, so this is, let it be defined as. Okay? So we can actually, so the equation that was for the psi dot will be simply equal to V bar, right? And you can actually show that mass multiplied by the V bar, okay, dot, from the equations from before, I'm using all of the properties of the rotation matrix and how R dot is related to omega and so on and so forth. You can actually show that this is, in the end, simply R from B to S multiplied by the forces in the B frame. Okay. And usually you'll find this is a starting point in a lot of robotics, papers. They say the equation of motion of a rigid body, simply this is the translational part and this is the rotational part. First observation is that rotational is completely independent from translation. You see here? The rotational dynamics, they only depend on the torques applied. Okay? They live on their own. So SO3 dynamics is completely independent from the R3 dynamics. You remember SE3 had an SO3 part and an R3 part. The dynamics on SO3 is completely independent from what happens on the R3. But what happens on the R3 depends on the SO3. You see it in this form of the equation. You also see it in that form of the equation. You see here when I had psi dot is equal to R multiplied by the V, and the V dot is actually takes the angular velocity into account. There's a cross product there. So the rotational dynamics, they live on their own. The translational dynamics, they depend on the rotational dynamics. Okay? That's why you find usually in control as a strategy, they sometimes design a controller for the attitude, and then they design another controller for the position, okay, separately. And they have it like in a cascaded form, just because of this fact. Okay. Now how much time I have? We have 3 minutes, and this is the best part of the lecture, which is, sorry? The ending, yeah. So it's the most confusing part. Why not take this angular velocity and this V bar? And the V bar is nothing else than this guy, right? Is this a twist? Is this what we call a twist? On the top, angular velocity. On the bottom, velocity, linear velocity. So it's a twist, right? If you always think that twists are just angular velocity on the top and linear velocity on the bottom, and everything is, just what you know from previous, other courses, that's not the case. This is not a twist. Okay, I'll confuse you even more. You see this V bar? A question to you. Is V bar, which is equivalent to the psi dot, is it equal to V from B to S expressed in S? You see here, I have V, B, S expressed in B. Then I take the rotation matrix to multiply it from B to S. And I say this is the V bar. Isn't this taking the vector B to S expressed in B and expressing it in the S frame? So it should be something like this, right? Okay, that's a good question. So this V I'm writing here, okay, this is always a confusing part. Actually, it's a small v. It's so it's like this part of the twist. And the answer is no, it's not. Quick proof, okay, in 1 minute. Okay. What was the relation between the capital V, the twist in the S frame, and the twist in the B frame? What was the relation? Adjoint from where to where? From B to S. Okay. What is this? What are the components of this twist? It's this guy and this guy. You all agree? What are the components of that guy and V? And here there was R0, R, psi tilde, and R. Of course, the indices will have the same indices here. Show for yourself that, okay, that V, B, so this is the small one. Actually, I'm going to color it so that we don't. Actually, it's there. V, B, S. S, so it's actually this one. Is equivalent to, by just expanding this expression, is simply equivalent to R, BS, VB plus psi tilde multiplied by VB, BS. Okay. And now the omega, right? This one should be, wait a second. No, it's V. Yeah, okay, wait, yeah, you're right. Yeah, exactly. So this one, yeah, it should be omega, yes, sorry. It should be omega, right? That's correct, yeah. So this one multiplied by that, plus this one multiplied by that, okay? So what is this first expression? The V bar. And what about this expression? It is the cross product between the vector psi and here you have what? What is this expression you see here? It's actually the omega BS in S. You see the omega BS in S is actually R multiplied by this guy and 0 multiplied by that guy. So here I have omega BS in S. And actually this V bar, we said that if you go back, now you can actually, this is part of the assignment also, you're going to find that the V bar is nothing else than actually the V dot. Sorry, the psi dot. Okay. So this is actually what the V is. So the first conclusion is that this V, this part of the twist has nothing to do with the V bar. It's not the same thing. Yes. Psi in the second line, yes. Assignment, if you have, this is a vector, and it's multiplied by the skew-symmetric matrix, it's equivalent to the cross product of the two vectors. The assignment problem. You had in the assignment x tilde y, it's equivalent to x cross product with y. Yes.
Shouldn't these, the other stuff after the plus, they be zero if the frame was on the center of mass?
Here? No. This is the psi of where the frame is. There is no center of mass here at all. Okay. Now the conclusion is that, have you seen this expression before? The answer is yes, you have seen it. Okay. You see when you remember what you were discussing about when you take the position and you derive it and you get an extra term, a coupling between the rotation and the translation, and the position comes into place. You see, this is like the rate of change of the position, while this term is actually the tangential velocity. You had something like a normal velocity and a tangential velocity. This is actually a tangential velocity, which is the cross product between the omega and the psi. It makes sense that you forgot this stuff. That's actually good news, okay, for you, okay, because it's useless, because it's very hard to work with in real applications. What I'm doing right now is that I'm showing you that all of this stuff, and even all of this stuff related to Coriolis and gyroscopic terms and all of this complicated stuff, is all incorporated in this very simple equation. They're all just encapsulated in one term. You know exactly how it changes coordinates from any frame to any frame, and you can do everything in this simple expression by just preserving the fact that you're using a twist, and the twist has a group structure and blah, 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 blah. Okay? I'll stop the lecture and I'll take questions, okay? So if someone wants to leave, okay? جزاكم الله خير. That's the end of topic number 2. After next week, inshallah, we're going to be starting taking this stuff and doing robotics with it, inshallah.